Well, here in week 2, lesson 5, we present yet another system of syllogistic reasoning. It's called propositional logic, sometimes called statement logic, sometimes even called symbolic logic. That'll become obvious to you in a few minutes when you see the symbols. Now, don't worry. This week, we're only going to present the structure of propositional logic. Next week, week 3, we're going to be doing an autopsy on both the 5 categorical syllogistic forms that you have now mastered, as well as an autopsy on these 5 propositional logic rules of inference that we're going to examine today. So in preparation for exam number 2 that's coming up, you'll only be required to identify the structure of propositional logic, just as you'll be required to understand the structure of categorical logic, the 5 forms, the 5 valid forms in each category. So what is propositional logic? Well, we always start with definitions. And in the book, beginning on page 95, you might want to check that. And we find this definition. So the definition of a propositional logic is this. It's the formal logical system that uses symbols representing propositions as atomic units related to each other by connectives called logical operators. So for instance, if I wanted to say, if I win the lottery, then I'm rich, there are 2 propositions there. I win the lottery and I'm rich. So I might use P and Q to symbolize those propositions. We'll see that in a moment. The operators are referred to as not, and, or, if, then, etc. Now, these are common connectives, logical connectives that we use in everyday language. When a child learns English language or any language, actually any language, you'll find all of these connectives are present in every language in the human experience. Now, there are 5 special logical symbols that connect the propositions within the premises. First of all, we have the tilde, which symbolizes not, the dot, which symbolizes and, the wedge or the V, which symbolizes or, and the horseshoe, which symbolizes if and then, the structure if then. Then there's the triple barb, which is the symbol for if and only if, and the material implication. And here's how we'll properly read these symbols. For any statements P or Q, let's just use if I win the lottery as P, and then Q is going to be representing then I'm rich. Here are the following compound statements. It is not the case that I win the lottery. So I would symbolize that by tilde, not P. Okay, that's how I would symbolize that. If I've said it's both the case that I win the lottery and I'm rich, I would symbolize it by using the dot. If I said either I win the lottery or I'm rich, I would symbolize it by the V or the wedge. But if I said if I win the lottery, then I am rich, I would say if P, then Q. And finally, the most stringent tautology of all the symbols that we study is going to be the if I win the lottery, if and only if I win the lottery, then I'm rich. Very, very stringent. Now, in common language, this chain of reasoning is called a sorites, from the Greek word soros, which means heap or stack. In propositional logic, there is a rule called hypothetical syllogism. This is a very common structure. We use this all the time. If A is the case, then B is the case. If B is the case, then C is the case. And then therefore, if A is the case, then C is the case. You can see that structure right here. And here's where it becomes symbolic. You can see that. And here's how you read that. If A, then B. If B, then C. Therefore, if A, then C. That's how you do it. And we invoke these rules to construct formal proofs for the following arguments. Let's just choose a simple but yet complicated argument, and see how we use this all the time. If you've taken the GRE, the graduate record exams, you probably have seen this. If you have taken the SATs, you probably have seen this in the reasoning and the analytic parts of these, but this is the logic. Let's just take this for an example. How would we prove the validity of this argument? First of all, by reading it in ordinary English and then symbolizing it in propositional logic or symbolic logic. Here we go. So we read, if Alex is the baby's mother, then Brady is the baby's father. And if Brady is the baby's father, then Chuck is the baby's uncle. If Chuck is the baby's uncle, then Lydia is the baby's aunt. But Lydia is not the baby's aunt. That's the key proposition right there. Lydia is not the baby's aunt. Because what does that do? If Lydia is not the baby's aunt, then Chuck is not the baby's uncle by one of the rules called modus tollens. The final premise here in this chain argument is either Alice is the baby's mother or Ellen is the baby's mother. Therefore, Ellen is the baby's mother. So if we symbolize all of that into a formal proof, now don't try to get the formal proof part of this. We'll get that next week in week number 3. But here's what it would look like. Step A, if A, then B, if B, then C. Well, that's a hypothetical syllogism. That's one of the rules. Step 3, if C is the case, then L is the case. Step 4, Lydia is not the baby's aunt. Remember, I told you that was the key. Step 5, either Alice is the baby's aunt or Ellen is the baby's aunt, therefore Ellen is the baby's aunt. Now we can see here that if we understand the rules of logic, the 5 rules of logic, propositional logic that we're presenting, we would understand that this is a valid argument. And the key is step number 4, because it denies that Lydia is the baby's aunt. And that has consequences. And so all we need to do for today is to present the 5 rules. We're going to pause right now and get those up here. Pause. Let me do pause. We're going to pause. So here are the 5 rules for natural inference that we're going to be using in propositional logic. There are 19 of them, but unless you're doing game theory, next week we will show you an application in game theory, video game theory, or unless you're designing microchips, like my friend David designs, you probably wouldn't need any more than these first 5. These are the most common usage of propositional logic. So we have modus ponens. If P is the case, then Q is the case. That's premise 1. Premise 2, P is the case, therefore Q is the case. That makes natural sense to us. Modus tollens also makes natural sense. If P is the case, then Q is the case, not Q. Therefore, not P. Disjunctive syllogism. Either P is true or Q is true. Second premise, P is not true. Therefore, what? Q is true. The conjunction. P and Q, therefore P and Q. And hypothetical syllogism. If P is the case and Q is the case, if Q is the case, then R is the case. Therefore, if P is the case, then R is the case. Now, these exhaust all 5 of the formulas that we're considering in propositional logic. So the only thing you'll be required to do for exam number 2 is to understand these 5 rules and their structure. In week number 3 and in week number 4, we will be actually using these to both formulate valid proofs and showing you how this is the case. And we'll also be using these to refute other arguments, arguments opposed to your arguments. And that's the beauty of understanding both categorical syllogisms and propositional logic syllogisms. because for very simple arguments, we use categorical logic. We use those syllogisms, the 5 that we're studying. And if we have complex, complicated, intricate structures like we examined today, with Ellen being the baby's aunt, then we use propositional logic because it allows us to examine many, many levels. As you can see, the intricacies of propositional logic allow for literally hundreds of premises leading to a conclusion. And then next week, in week number 3, we'll show you how to test for validity using truth tables. Very simple idea, truth tables. Anyway, good luck on exam number 3.